All right, looks like I'm back. Let me just check the stream, make sure everything is good. Yeah, I think I'm back here. So I have finished, I'm using air quotes here, finished the problem sets for 804 quantum mechanics. Now, by finished, I mean I've at least attempted pretty much all the questions. There were a couple questions that I skipped over, I think in the first 5 problem sets, because one of them required watching a super long video, which I didn't want to watch. Then it was like an hour-long demonstration of some experiment. And then the other one, which I also hadn't downloaded. And I like to have stuff downloaded so that I'm not using my bandwidth downloading a video while I'm also uploading this live stream. And then there were a couple others that I hadn't installed Java yet on my computer, so I skipped over them. But other than that, I've basically seen the breadth of the questions. So that was really the goal of doing this, is I went through all the lectures, so I've at least covered all the content. And now I've gone through all the problem sets, so I've at least done some practice with the majority of the content of the course. Now, I still have some time left. I'm ahead of schedule in terms of, if I were a normal student, then maybe it would be like, all right, now it's time to do the exam. And when I was doing the MIT challenge, very often, even going through this process was enough to feel confident going forward on the exam. This, on the other hand, has been a very hard class. I've been kind of reflecting that this has definitely been hard. This is definitely a harder class than any class that I took during the MIT challenge. And I think the reason for that is twofold. One is that in general, in the MIT challenge, I found the classes that were physics-based harder than the ones that were computer science-based. I was more interested in learning computer science, so I didn't really sweat that too much, that, if I struggled a little bit with differential equations, or, my final grade for that class was a little bit shakier than, for some of my other classes. I was okay with that, because for me, my main goal was to get the computer science knowledge, and the other stuff was just to round out the degree, so to speak. Whereas this is sort of clearly in that direction. So it's building on something that I was already, I was a bit weaker in the MIT challenge. So the kind of foundation that I have is not quite as strong even for that. The second thing is just that it's been a long time since I've done this. So some of what I've been doing in this practice session is kind of getting up to speed with where I should have been when I started this. So some of that is from previous classes that I have done but have become rusty. So, forgetting how to do triple integrals over spherical coordinates, or, making a mess of common trigonomic identities, or Taylor expansions, or all of these kinds of tools, which I did learn. And when I see them again, I'm like, oh, right, I remember that. But when you're doing practice problems and you haven't done them for 8 years, they sometimes are a little slow. The other stuff is from this class itself. And I did not do 803, which was one of the prerequisites of this class. I don't want to say I regret not doing 803. I think that this has been fine without it, but it has been a little bit more relevant than I would have thought it was going to be. I thought that I could get away with not having done 803, but I think there's some stuff that was from 803 that is informing solutions here that is making it somewhat more challenging. Not everything. I don't think that I think the operator stuff is new. A lot of the specifics of quantum mechanics are new, but a lot of the stuff involving plane waves moving, sines and cosines, the differential equations, this stuff is from 803. I didn't do 803, so I'm struggling a little bit now. So these factors combined mean that this has been a harder class, and then that has shown with the amount of time I put into it. So with the MIT challenge for classes, I would say that most classes I was doing them in a full-time pace. Later in the challenge, I was spreading them out. So I was doing a couple classes in parallel, the way that you would do them as an actual student. But if I were to talk about time exclusively devoted per course, most of the classes were between 1 and 2 weeks. There was maybe a couple that were closer to the 1 weekend, and some that were closer to maybe even 3 weeks. But the ones that were closer to 3 weeks were also ones that weren't like this class. They usually involve projects. It just involves a lot of time. So if I had to build some software or something, that took a little bit more time. I spent a little bit longer on those classes. So the fact that, I'm now rounding up the 3rd full-time week of this class and I don't feel ready yet to pass the exam is just evidence of the challenge level of this class. And going through this thing, I'm not even confident that in the time I have remaining, I'll necessarily get to the level that I would like to be at. Now, I think what my goal is, and this is what I've been saying from the beginning, is that sometimes you're going to be facing a learning challenge that because your background knowledge, like what I was saying, is not strong enough, or you are coming at it from a weak point, so meaning that this is not a strength of yours, so it's harder for you than it might be for other people, or even just there's some other factor that's influencing it. It may be something that takes you longer or it takes you less time. So one of the things that I find nice about doing self-education projects versus projects where you have to do it at school is that school kind of says, this is how long this class should take. So this class should take you, 4 months while you're also doing 4 other classes. And if that pace is too fast for you, it feels overwhelming. You say to yourself, you know what, I'm dumb. I can't do this. This is for other people. And if the pace is like slower than what you can maximally handle, then you're like, this is easy. I'm super smart. And for self-education, because I'm doing this by myself, because I don't have any other person to compare it to, really, I'm aware that, there's going to be a certain amount of time this is going to require given my background, and I can do it as effectively and efficiently as possible. But at the end of the day, I still have to do the work. And so what I'm doing here is doing that work. And will I be able to get it done in a month? I'm not sure. Now, part of what I'm trying to do right now is to keep I haven't been trying to move the goalpost, so to speak. So even though I've basically, right from when I started this project, I became kind of aware that, whoa, my original month plan might be too fast. So I might not have enough time to get to where I want to go. And that can lead to a situation where, like, well, once you recognize that, maybe you should change your plan. Once you've learned that, maybe you should put in 6 weeks or 2 months. And there were 2 reasons I didn't change the plan. The first is that my schedule, you guys can't see my calendar, my daily life as it exists outside of this project. But my calendar was that I had carved out a chunk a month where I could mostly focus on this project. It's turned out to not be as clear cut as that. I've had to do more work than I thought I was going to do. But I had about this month to focus mostly on this project. Whereas I don't have 2 months. Once May rolls around, I have a bunch of other work. I have a book coming out. I've got to record the audio version. I've got to do various projects. So my time is not going to be as focused as this. So that's one reason that I can't just stretch and draw out the class. The other reason is I think that if you set a really challenging goal, now, if you set such a challenging goal that you just give up entirely on possibly making it, then that won't work. But if you set a challenging goal that you can possibly achieve it, if you work really hard, that's going to make you at about peak productivity. So some people in the comments were asking, how do I focus for so long? And a lot of it has to do with controlling these parameters of motivation. If I were doing this class and it was a breeze, meaning that I was getting all the questions right and the problem sets, oh, I'm going fine, I'm doing really well, then it's very likely that what would happen is I would, slow down my schedule as I don't really feel like staying. 2 hours is good for right now. I'm going to keep going. On the other hand, if it was the opposite, meaning that it was something that I felt like even if I put in my maximum effort, even if I was trying nonstop, there's no way I was going to succeed at this project, I'd also probably cut effort. I'd procrastinate. I would delay on it because there isn't this incentive structure for putting in the effort. So in your actual classes, in the actual things you're studying for, you're often not at this ideal difficulty. Sometimes you're going to be too easy. Sometimes you're going to be too hard, and you're going to not have that maximum amount of focus. Now, for me, I'm closer to the too hard end than the too easy end for this particular class. But I am also aware that if I really put in the effort, really work on it, I might be able to get close to where I want to go. Now, why does this matter? Well, it matters because even though I'm picking this particular goal of passing this class, if I step back for a moment, that wasn't really what got me here. I'm not getting credit from MIT. I'm not going to get a physics degree from them. No one's going to give me an A that I can put on my resume for doing this. So the whole reason for doing this in the first place was that I was interested in quantum mechanics. I wanted to understand some of the math behind it. So when people were talking about it, I was hearing it in, it comes up in lots of different things. It comes up in chemistry. It comes up in some biology, particularly in molecular biology. It comes up in quantum computing. A lot of these interesting fields, I wanted to understand it. And so I wanted that intuition. So given that I wanted that intuition, what does this test have to do with it? Well, the test is just a benchmark, meaning that if I were to get a perfect score on the test, that would mean I really, really understood it. But even if I didn't pass the test, even if I didn't get all the way that I wanted to go, I might still have some of that intuition. I might still have it, albeit imperfectly. And so when I'm thinking about this class and where I wanted to go with it, it's very clear to me that the closer I can get to being ready for this, the better off I will have been in investing this month's time. So I haven't tried to change the benchmarks, even though I've kind of quickly recognized that this is harder than I was expecting, or at least what I've experienced in the past. And we have our first visitor. Oh, yeah. Coming here to join me for studying, my friend's cat, who I'm cat sitting right now, joining me here at the computer. And so at the end of the day, what is this all about? And I think what I want to stress when I'm doing this project is that it's possible to look at something and be like, you know what, this is really hard and I don't know how the outcome is going to be, but I'm still going to put in my best effort. And I know that even if I don't reach the goal that I had set initially because I didn't have enough time to get there, I'm going to be further than if I had tried any other approach. So basically, if I keep this goal and I keep working on it with the idea that I want to pass, if I try the exam and I do fail, I'm going to have used this month a much better than I could have with any other approach. And this is not the end of the story. This month-long period of time is an introduction. Even if I had done it perfectly and I got 100% of the class, it wouldn't mean that I fully understood everything about quantum physics. This is 804. In MIT, they do 804, 805, 806. There's 3 classes of quantum physics. I was already only doing 1. So there's a whole bunch of problems and ideas and ways that this theory impacts reality that I haven't explored yet, that I haven't derived yet, that I don't fully understand. And so for me, whatever happens in this project, this is just going to be the beginning. So what I was hoping to show here is showing how you can approach your classes, how you can approach studying for something that you find particularly difficult, just the way that I find this difficult. And so now that I've gone the first pass, now that I've gone through the first lectures, what do I want to do? Well, what I want to do right now is I want to go through each of the problem sets with the solutions open, and I want to make a list of everything that I didn't get when I was doing it. So I'm going to have what I wrote down, and I'm going to have the solutions. And then I'm going to try my best to jot down what was the piece that was missing in order for me to solve this problem. Now, sometimes there's going to be multiple pieces, and sometimes the pieces it's obvious when you see it, but it's not obvious when you're doing it. So there's a little bit of a subtlety in doing this, because you can just say, oh, it needed this concept. But part of it is not just applying the concept once you know that that's the concept you need, but recognizing that you should have applied the concept. And that can be tricky, particularly with some of these derivations, some of these calculations, some of these integrals. There's a trick to them, and it's not always obvious. Like once you see the trick, it's obvious, but it's not always obvious what the trick would have been in looking forward into it. And so doing this with all the problem sets is not going to give me a complete picture of the course. So I'll just write out what I'm trying to do here on this piece of paper so that it's a little bit more clear. Let me just switch over to this view here. So basically, let's just say this is our box. I'm just going to call this is the view. So if you imagine, maybe I'll do this with pen because it'll be a bit easier to see. If you imagine that this is our box, and I'm going to call this box, 804 quantum mechanics. So this is 804. Quantum mechanics is probably some ambiguously defined region. So this would just be quantum mechanics. And this box is what we covered in this class. So already I'm dealing with a restricted subset of what was there to learn. Now, this is what was covered, let's say, on the problem sets. Now, the problem sets can't cover everything. So you probably have something like this, I would say, that covers. This would be problem sets. Now, I believe that there's good coverage for the problem set. So I mean that this area is pretty large compared to this, meaning that there wasn't a whole lot that I would need to know that was not tested somehow in the problem sets. The exam, for instance, is probably going to be smaller than this region and wholly contained in here. So we're probably going to have something more like this for the exam. Let's just sort of like, you know. Now this is kind of a hypothetical thing here, but let's say this dotted region is going to be exams. So now, meaning that if I only did the exams, I'm probably dealing with a strictly smaller subset of practice than what was covered in the problem set. There is some things that I think were just coming up from lectures or just from readings that maybe we didn't derive in the problem set. So there is going to be some stuff in here. So the problem sets are pretty good. Now that means that if I fully understand the problem sets, I should probably understand the exam. Now, some of the challenge of that is that even the problem sets in their actual solutions, so the things that you would have needed to solve them, are going to be some possible subset of this. So if I'm looking at doing over these problem sets again, I'll draw a new picture because this one's getting a little bit cluttered. If I'm doing a new picture, let's say these are the techniques that were actually needed on the problem set. These are all the techniques that we're going to cover. And this was just some sort of random subset of this, right? So this is just some random smaller subset of actual problems and possible problems. Now, because this is a random subset, if I go through these problems once, I've probably got good coverage of this on average. It's probably not going to be the case that there's a lot of stuff missing from this. However, if I do the actual problems here, I've probably got a pretty good estimate of my ability on the test. So if I, let's say, do these once, let's say I do these once, and let's say, you know, I get some sort of score. Let's say I understood about 30% of this going through it once. I know, because this is probably a random sample, that this therefore means that I probably understood around 30% of this, which, because it's also related to the exam, is probably around 30% of the exam stuff. Right? Does that make sense? However, if I continue to study this, so I continue to study only this, well, I maybe get, let's say I get close to 100% on this now. But now, because I know what this thing is, I'm not doing a random sample anymore, then there's going to be some region that doesn't get covered. So my estimate for how well I would do on this is going to go up, but it's only going to go up. It's not going to go, it's going to go up by the proportion that this are related to the area that this covers in the gap. So if this area of these problem sets, so let's say the problem set area, let's say it was, I don't know, so it was 80%. Then if I went from 30% to 100%, well, I was going from 30% of this 80% area. And because this was a random sample, I'm probably doing about 30% of the 20% that wasn't covered. But if I really practice, then now I'm 100% of this 80% area, but I'm still only about 30% of this 20% area. So I've improved my score, but not perfectly. And so the question is just, how much is this area compared to this area? So if the actual problems were quite small, so if we were dealing with, let's say the problems only, they only covered about 10% of what you would need to know, right? If they only covered about 10% of what you need to know, then you could spend a lot of time improving this, but you'd only improve your grade by, let's say, you know, a few percentage points by just continually, repeatedly studying these things. So I have to have a balance here. At some level, and I'm drawing this as a surface, but really, these are kind of a hierarchy. So really what we can think about it is, I know this is already getting a little complicated. I'm doing this live, so I think if I had some time to prepare it, I'd work on a bit better visuals. But what we're really looking at is, let's say that there's a concept layer. I'll say concept, and then I'll put technique. And these are probably multiple layers. So there's going to be some kind of higher level concepts. So imagine these are surfaces here. And then there's, you know, various techniques. Now, it could be that the problem sets cover basically all of this higher area here. So this could be, I'm just going to just put this for problem sets. And it could be that here they cover a good proportion of the higher level concepts. But just because these areas expand as you go down, when you get down to more and more smaller techniques, you're going to get smaller and smaller areas that are covered by these problem sets until we're like this, you know. Now, I don't know whether this is exactly how it works, but essentially what this means is at the very high level, I'm quite confident that the problem sets that I did covered pretty much all of the material. So at the high level, near 100% coverage. But at a low level, it's going to be much lower. Now, I don't know how low it is. It's probably not like a few percent, but it's a lower percentage just because I didn't have to use every single trigonometry identity that could be useful here. I didn't have to use every single little trick of calculus or trick of algebra or things to get to this thing. I'd use quite a few. So for this kind of class, I don't know, like maybe it's like 50%, but it's not 100%. And so this kind of fits in with what I was showing here about the problems, is that if I just go through and I master these things here, if I focus on the higher areas to master, I'm going to get better coverage. But if I focus on the very small details, I'm going to have weaker coverage. And what is that going to mean when you do an exam? Well, when you do an exam, because the exam is a different subset, so I'm just practicing the same subset over and over again. If I have focused on this layer up here and I've really understood it, then I'm probably going to have pretty close to the score that I got in there. So if I go from, let's say, 30% on the problem sets, which are that shaded area here, and I go to, let's say I go to 80% or let's say 90%. So I really studied it and I now really understand that 90%. Well, at the high level concepts, I should be nearing 90% now. So at the high level, I should be nearing 90%. Whereas if I focus on the most low level techniques, then there's going to be a lot of stuff that I get better at, but there's going to be a lot of stuff that I didn't cover. So maybe if it's 50-50, like I'm just estimating here, it might be 50-50. Then if I went from 30% to 90%, well, then this was sort of my estimator of how well I understood it. Well, it's going to be 30%, and then this is going to now go to 90% if we had about 100% coverage. Whereas if it was only 50% coverage, well, then I've gone from 30% to 90% for that 50% subset. So that's going to go from, well, what's that, 15 to 45%. So we're going to go from 15 to 45%, but this one's still going to be 30%. So I've gone from 30% maybe now only to 75%. And this is still an improvement, but it's important to recognize why I'm not getting a perfect thing just by reviewing the problem sets, because the problem sets were drawn from a sample from all the possible things I would have known. And the higher level concepts, the smaller the space of things that you really needed to understand. And so this hierarchical representation means that when I'm going through the case, what I'm going to want to look for is either concepts that are up here. So did I understand operators? Did I understand what it means to be a Hermitian operator, orthogonality of the eigenbases, these kinds of things? Up here, did I understand these concepts? And less so, oh, for this particular problem, you need to know this identity that uses the cotangent, right? Now, there is ways of grouping these things, so we do need to master these techniques. So what I try to think of is, even though there was only one of them on a particular test, you can see these as being a family of related techniques. So for instance, Taylor expansion is an example of a technique that maybe there was a particular way to use it with a particular outcome, but don't memorize that. Just understand that we are having Taylor expansion or Taylor series. So in a certain way, your techniques can also bubble up to being these higher level concepts if you see them and practice them as a family of doing this. So what does this all mean? Well, this means that I'm going to be going through these problem sets with this idea in mind, that I want to go through it, write down what concepts I'm missing, but as much as possible, I'm trying to pick concepts at this level. And I'm also, if there's techniques or there's technical things that need to be worked out, which there obviously will be, then I'm going to want to be trying to pick families of techniques, not just memorizing the specific, this was the question and this was the answer. I mean, if you get down to really, really low, so we're not even talking about techniques, this could just be like answers for problems. Well, and obviously the solution space, these are impossibly small, you know? Like if you just memorize, oh, the answer to this particular question is 7, that there's no insight there. There's no understanding. So this is why, because of this hierarchy, because of this coverage, I feel like if I go through the actual problem sets with an eye to this higher level concepts and techniques, and I master those, then I'm much more likely to transfer that mastery to the exam than if I focus on very low level details. Like this was the exact way to solve this particular problem. It was, what was the general approach to solving this problem? And so there's a few ways that you can talk about looking at what you got wrong and figure out, how do you generalize this? How do you generalize the error that you made to think about it at a higher level, so that when you're going through the problems, you're not dealing with it at this low level where you had relatively sparse coverage. You're dealing at this high level where you had relatively high coverage. And this is the right way to think about these kind of hierarchical math-based classes generally, I believe, is to think about them in terms of, you're always wanting to try to integrate, to move things up towards broader principles, broader ideas. You do need to master techniques, but when you master techniques, it's often better to even think about them in terms of families of techniques, so that instead of just one set of trigonomic identities and there was only one of them covered, you recognize, well, there's about these 15 that are all about similar level of obscurity that I should really have memorized, even though they didn't show up in any of those questions. So with that in mind, I want to switch now over to going over everything, being careful about what did I get wrong in these problem sets? Why did I get it wrong? And trying to be mindful of this. So this is a little bit of a digression. I haven't been trying to talk too much because I'm mostly focusing on the studying, but I felt like this was a worthwhile break, because I think this is a very easy thing to not get right or not understand about what the difference between problem sets and the exam are actually going to be, or what it means to understand things in terms of having things being random samples of possible spaces. All right. Now, it is also possible, I will state that the problem sets are unlikely to be a random sampling of things like that are going to be related to the exam. I think the exam is probably going to be easier. So there's going to be some problems that I can be fairly confident are not going to be on the exam because they would have been too hard for the time constraints. But there's other problems that would certainly have been on there. And so that there's probably some things that I can avoid putting down here, even if I got them wrong, just because I don't think they're going to be relevant to that particular purpose. And in my mind, because I'm leaning more towards intuition than practical application, I think the exam is a bit of a better basis. If I was actually going to go do experiments and calculate numerical values and do this kind of stuff, then I might even want to go in the other direction and emphasize those versus this kind of theoretical understanding. But given that I'm probably never going to handwork a problem and I want the intuition, I want to deal at that more conceptual level, principle-based level, and not at the calculating level. So let's go through now, and I'm going to not do this on here. I'm going to do this on a separate piece of paper, I believe, just because I think it will be a little bit easier to refer back and forth. So I've got a couple sheets here, and what I'm going to do is just write down So normally I would divide these into columns and do concepts, facts, skills, but I don't think that's particularly useful right now because I haven't gone through it to make sure that I'm clear on the distinction. So what I'm just going to do is I'm just going to write them all down first, and then I'm going to kind of, from that, get a sense of what's the best way to practice it. So let's go, I'm just going to call this things to master. And I'm going to do it through the problem sets. All right, all the way back to problem set 1. So I can close this because I was not working in that book at that time. And open up my problem set 1 notes. This is also why I was making little notes when I was doing the problem sets. I probably should have made more notes in retrospect of what I didn't understand about the question, just so that it doesn't take me as long to figure it out when I'm going through it any other time. But all right, so here we go. Problem set 1. You know what? I'm going to transfer this over, and I'm going to switch over here, and I'm going to put the solutions here. All right, let's go problem set 1 solutions. Now, this one I didn't do, so I'm just going to make, for questions I didn't do, I want to maybe make a different, I'm just going to put, I'm going to maybe make a little questions to do. And I'm just going to put 1.1 here because I didn't do that one. I'll put those separately. Where we got problem set 2. So I did work on this one, but I didn't finish it, and I didn't look at the feedback. So I might go back and do that later, but I would put classical electron orbit. To A. So this was dimensional analysis. I did require some work there, but I feel like I've gotten it better now. So I will put, I'll just write dimensional analysis. Actually, I need to have the questions too. I can't just look at the solution. All right. Okay. I think I got this one right. IV. Hold on a sec. This is just numerical calculations. I think I got these right. I don't have any pen here. I was not as good about using the pen for answers before here. But I think I got these right, or if not, they were like roughly right. Yes, this is dimensional analysis. I think I can just skip over this. Question 3, where's 3? I think this was also okay. So I'm going to just put de Broglie. Okay, because there's a little bit of confusion I think I was having about wavelength versus velocity for these things, because I wasn't sure whether it should be C or something like that. Question 4, okay, double slit. I think I've gotten better at this, but this was definitely, I'm going to put so I did not have the formulas right for this, but I think it will be okay. I'm just going to write it down right now. Double slit interference. Is there any technical tricks here? I don't see any written in pen right now. And single slit, I think I've done these since, so I might be able to check these off, but I will put them just in case. And question 5 I didn't do, so this is 1.5. And then what was, yeah, question 6 was this single slit. Okay, so that's problem set 1, problem set 2. What's the difference between phase velocity and group velocity? How do they differ in gravity? Okay, so this is definitely something that I had not done. So let's go. I think, again, I've done this, though. Oh, this is problem set 1. I'm just gonna put here. So I'm going to just put a little check mark in pencil right here next to the ones that I have done some work on since the problem set. So I'm just going to put phase and group velocity dispersal relation. So I think I did this. Okay, and then the question 2, we have these things. I think these things will be fine. Three 3A. Okay, we got that one right. This is more dimensional analysis. I'm just going to put in brackets here. This is all right. 4A. No, left unchecked. Did I not do this one? For so I'll put this 2. Did I do any of the other ones? No, I went right over. So I'll just do 2.4 here. So I can skip over this. Delta functions. Okay, there was some just basic math errors here. All right, okay, our first technique here was in delta function B3. I'm going to put delta integrating, and also I'm going to put substitution of variables to solve integrals. That's the same problem. I'm going to put working with limits. Okay. This is, which one is this? Changing the order. Changing order of integration. All right, I got these ones basically right. Oh, great, we've got construction back. Oh, I don't think I updated it. Oops, sorry guys. So what did I get wrong here? These are just basic integrals. I'll just put definite integrals here. Although I probably should put a check mark next to that because that's something I've gotten a lot of practice on since. Question is this 7? It says this is x7. Okay, I'm going to leave that. And then 8. What do we have here? So I'm going to put hyperbolic sine waves. Okay, this one there were some mistakes, I think, due to trigonometry. So let's look at what actually I missed here. Okay, I'm just going to leave this at hyperbolic sine cosine. It's again change of variables. So when I do I change of variables here as well? Yeah, change of variables. I'm just going to put I don't want to do a check mark because I'm already doing that for solve. I'm just going to put let's put a dot next to it when I see it again. All right, let's go to problem set 3 now. Operators. Okay. B, what are the eigenfunctions? Okay, these were pretty close. Square integral. Okay, this is... I'm just going to write square. I think it's fine. I don't need to put square normalizability. I would like delta function normalizability because I think that was something that was in there, but I haven't gotten to that point yet. And maybe I'll just write it down. Just delta function normalizability. All right, we're already now Taylor series expansion. So Taylor series expansion. I think Fourier transforms on my list here. Yeah. So I don't need to memorize that. Meaning of the commutator. How did I get to that part here? Where's F? F. Derivative operator. So what did I screw up here? Yeah, I think this is also Taylor series stuff. G. Let's look at G more closely. Question 2. G. I'll just put operators. 1. Okay. H. Minus e of x. Okay, and for f of k. Yeah, that should be fine. Because this is just... Uh, 3. Commutator, all right, for 3. Okay. 4. A was right. B was... Okay, B was, can you explain, can B interpret any common eigenfunctions? If not, explain why. I think I'm going to put commutator and eigenfunctions, but I think I've learned this since. Just going to put a check mark there. Okay. Okay. Problem set 4. Oh, this was problem set 3. Where did I? Oops, where did I do? Oops. I added it without separating them off. I'm just going to put and 3 here. Save myself the time of going back and rechecking that. P set 4. Problem set 4. Simultaneous eigenstates 1. I think this is just I did get this wrong, but I think this is just something I understand now, so I don't think there's much to put in there. Okay, I'll put always have real energy eigenstates. B Okay, this is a related point. Three A. Here. Time evolution. F. Construct another normalized wave function. Okay, I'll just do it. Find orthonormality. Product. So this is going to be problem set 4, which I did not do. Qualitative form of function in VFX. No, we're problem set 5. Problem set 5. So this one was just a calculating thing. I'm just going to put redo. Let's redo 5.1. Should go back to this folks for him. But this is just something to redo, I think. To So we've done this. This is, yeah, classic harmonic oscillator. Just put comparing quantum simple harmonic oscillators. Three. Ba, 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 ba. So I'd forgotten the phase here. Okay, and then there was all real energy eigenstates was how we solve this. Just gonna put blanks to solve. Da, da, da. I think maybe I did this another time. I'm gonna finish this now. And I want to here. Real. Okay, so this is the same thing I struggled with last time. So here was something that I'm going to do this. 5.3b. Because there was something I didn't understand here. 5.3. Is this the solution? 3. I think they just did a I just knew that integral. So I'm going to write that down. Integrals of Gaussians. Okay. Operator method. Question is this C? Looks like there are some trigonomic identities here. This is C. Where's C? You can see this is 5C. 5.3B. Is this 3 again? Is this still 3? Still 3. Yeah. 5.3 B C. Okay. I'm just gonna put adding. Unmuting through. Da-da-da. Okay. this the same? C. N operator, E operator. I'm just gonna, I'm gonna rewrite this as the actual equation. So N operator equal to E hat omega minus 1/2, and then I'm gonna have E equal to A dagger A, something like that, right? H bar omega. Okay, what do I have here? It's question E. This is going to be 4E. I think I just forgot square roots here. Yeah, I think that's it. Now let's go. Do problem set 6 over here. Problem set 6. That is right. That was a trivial mistake here. This one right. All right. Did I not do this? Apply it. And we did not. I think I did. Yeah, I know I did do it. Okay. I'm going to put 6.4 C. 5 quantum glue. Which question is this? This is 5. So I'm going to put 6.5 A. Again, hyperbolic sine, cosine, tan. Do a circle on that. All right. But this is 6. Where's the force argument? How does the energy include upon 6 A E? 6A Hermitian operators and commutators. All right. That seems pretty obvious. G. So we have 6, 6, G. G. I'm gonna go G. Yeah. All right. Problems at 7. All right. That's just a basic integration error. Okay, I got these right. 3. I'm gonna put this 3. This is 7. 3 B. B and E. Okay. All right. Matrices. 7. Point. Question is this 7.4. C. A. A. the I'm just going to put this as all rather than split hairs here. Problem set 8. And what is this one? Eight, 1, C. Okay. Two. That's right. And then we have right, and then 3 around Z. That's right. Okay, this is just a bunch of math. I'm just gonna, yeah, I've got commuting through in there already. I'll just put a second one. I did get these eventually though. Spherical coordinates. Question we on now? 4. This is A. Is 4A. 4A minus 3, 4. 4A. I'm just going to put trig integration here. Oh, thanks, Reed. I didn't notice some of your things. Reed's asking why I'm writing down some concepts and not others. So it's a little bit arbitrary, but sometimes I'm looking at things and it's something that I feel like I got from getting the solution. And then other times there's something that is, so one of them here, oh, integration by parts. That's a good one to put down. I'll put it where I put the other ones here with the, yeah, integrating by parts. I need to get better with that too. Oh, I can't really quite see this, what I got here. So yeah, I'm not writing down literally every single detail. Mostly this is just trying to become a good list of things that I'm going to go through. I've written down some of them. I've written down questions to redo, meaning that I felt like rather than try to do concept testing in another way, better just to tackle that question again. And then another time I'm trying to put down concepts that I want to work on. So there is going to be obviously things that I miss in this list, something that was important that maybe I didn't jot down, or something that like Reed said here about me just putting knowing the integrals of these Gaussians against, x to the n. He's correct that you can do the integrating by parts. And so instead of memorizing those, perhaps I should do the integrating by parts. That's something that I'm also going to dig into, because sometimes when you start doing them, you start recognizing, oh, I can do it in another way. But the goal here is to just get a good list of things to work on. Some of these I'm not going to work on, so I'm writing them down, and then already I know I've checkmarked some of them because I've already gone through them after doing them on the problem set. And then others here I might not do again because I feel like I've gotten some practice with them, but I'm just trying to get a little bit of a coverage, and then I'll pick which ones I want to do based on kind of what things seem to be working harder and whatnot. So I'm looking at I am also looking at you can't quite see it here. It's a little bit off to the side. Unfortunately, I'm working on kind of a small space. So I'm also going through my old problem sets here, and that's sort of also how I'm figuring out what I'm putting in and what I'm ignoring. It's a little bit challenging to display everything on the screen sometimes. But this is all stuff that I have covered on video here before, and I will try to scan these when I'm done. So if, you know, for the record, if anyone's wondering what the heck I'm doing. All right. Where am I going here? This is for, I think, I did some spherical coordinates here. I think this was a little bit of a detour I didn't need exactly. So this one here was, if I'm not mistaken, they used Mathematica for this. So I think I'm going to ignore that. Let me look here. Let's go 8.5. A. This was just a simple mistake here. And 6. What happened to 6? Did I not do 6? Did I skip over this one? No, what am I missing here? I think I maybe skipped this question. So we put 8.6. This question's to do. I should put them on the to do end, because I never did 8.6. All right, 9. Yeah, Reed's asking what I'm doing here. So one of the things, if you watch, this stream will be available as a video once it's done. And at the beginning, I kind of explaining what I'm doing and why I'm doing it this way. So anyone who's looking at this now can go back and watch the beginning, and I give a little bit of a discussion of that. So solving for x, y. Yeah, there's definitely some stuff with trigonometry that I don't feel as comfortable on. Honestly, when I was doing it, I remember doing it in the MIT challenge and being like, yeah, I'm not going to memorize all these trig identities. And now I'm kind of like hitting myself in the head with it, because I just sort of figured, oh, well, this will be something to look up later. It's no point memorizing all these trig identities. And now I need them. So that was also problem set 8. I'm not doing a great job at separating these out. All right. P set 9. Yeah, so one of the things is that I'm probably not going to do everything on this list, and I might do some stuff that's not on this list. The idea here is just to get a good review of everything. And once you can kind of see it in review, you can kind of get a sense of where you want to focus your effort. There's stuff here that, you know, I feel pretty good about. Maybe I got it wrong the first time through, but I feel pretty good about now, because a lot of this stuff is cumulative. So some of the earlier stuff that I found challenging, I think is kind of obvious now, just because I've done these other 10 problem sets. There's other stuff that's still going to be really hard. So problem set 9. Okay. Oh yeah, this was the infamous 51 that I couldn't figure out why the heck they got 51 here. If I look problem set 9 solution, they get this c squared, which they get 1 over 5. And so c squared is 1 over 5, and then bam, 1 over 51. I cannot for the life of me figure out why they're getting 51 here and not 25. I just guessed it was a typo, but or there's something that's like they think is super obvious, but it's not as obvious for me, because 1/5 squared is 1 over 25. It's not 1 over 51. Yeah, hopefully a typo. Hopefully I'm not missing some deep conceptual point. These these sheets, though, I've been a little less than trustworthy about them because a lot of the latex in the PDF is not rendering properly. So sometimes it's dropping an h bar squared, or it's an equal sign is a minus, and it has been frustrating because sometimes I'll be reading the question, I won't notice that they've omitted one of the symbols in the definition, and then the answer has it and I missed it. So it hasn't been a really bad problem for too much, but it is something I got to be careful about. It's just that these are not perfect documents. So here, going through this, I think I got this. Okay, let me get some. Just gonna put. These would be eigenvalues. I'm gonna put eigenvalues of L, LZ, and L squared operators. All right, 2A. Oh god, this one was just a mess. This Laguerre polynomial stuff. All right, so do I want to try this again? So I'm just going to put that up here. 9.2. Let's do all of it. Were there any tricks here? This one should have been solvable. I think it's not all, just A, I think is fine. I got that. B3. Oh, right. This is one where I was off by 1/2 factor. I think I got to put in the eigenstates equations of Coulomb potential. Coulomb potential is definitely what I need to do. Okay. Oh, this fine structure. Yeah. Okay. I'll put here this just so you guys can see what was required to get this one. Calculating the fine structure constant. This was just a hideous calculation. A lot of crazy like substitution and this kind of thing to get it out. So I don't think I'm going to focus on that. I wish I understood that better, but this one was just a hideous mess, and there's no way I'm going to have to do that on an exam. That was definitely the hardest calculation, I think, of the whole course. Now where are we here? I made a mistake here on 4E. How much angular momentum will it be? I'm just going to put that in my list of what's new. We do 9.4 E. And yeah, let's go. Let's just do angular. I just want to do angular momentum a little bit more, generally speaking. So F. Resulting radiation have. Yeah, let's go EF. Let's do that one as well. Oh, this cat has just been coming here nonstop. Hey, Milky, you gonna help me study quantum mechanics?
Come over here.
Just leave him. Just leave him. He'll come down.
Why is this green thing here?
Green thing? Oh, he was sitting here. I just put him in there.
Oh.
Where are we? Okay, 5. 5, I think, was good. Oh, yeah, this was just plotting one, so I think it was mostly... Oh, I need to revisit. What do I need to revisit? I shouldn't say it so quickly. This is just dimensional analysis. Dimensional analysis, dimensional analysis, dimensional analysis. So that's just got to be something I got to practice. All right. Problems at 10. All right. Oh, this was one where I just did the calculations slightly wrong for this too. And I was off by a little bit because I was rounding, and I thought I was supposed to be way off, but I was off by only a little bit. I just didn't calculate it right, and I thought, well, I've got the question completely wrong, but I just computed it. I just rounded a little too much when I was doing it on, in my head, and that's why it didn't work. 3. Oh, identical particles. So let me just go 10. Let's do 10. Not 10.3. This one here is not a calculating one. Let's do 10.4. Yeah. 10.4. Yeah. For all. Yeah. The identical particles, I think, is a big concept that I'm not doing too well right now. Crystal momentum, another concept that I'm not doing too well on. Which question is this? This is D. Crystal momentum. This one was just a little bit of calculus that I was screwing up, I think. What was I missing? I'll just do the question again. I think 10.5. I want to do A. Yeah, I think I got B right, so I can just do, yeah. It's just 10.5A. I'll do it again. Group velocity and effective mass. I just skipped this question? I think I maybe just skipped this question. Is rounds in 10? Yeah. Okay, so we'll do 10. 6 and solution 10.6. What do I not understand in order to do this one? Let me just look at the answer and see if I can write down the concepts that I need to understand. So I need to get crystal momentum. I can never spell momentum. I'll put also EQ. All right. Okay, this one was another one that I should just do again. 10.7. Yeah, 10.7. A. I think I got the other two right. Let's just do 10.7 again. 7. Yeah. I think this one's just worth redoing. Another thing with hyperbolic sines and cosines. Oh, and this one here. I just did this one this morning. I think I'm going to just skip this one for the old. Okay. Oh, this is problem set 9 and 10. So this is my list of stuff that I this is my list of stuff that I got from switch it up here. I think I can't quite show the whole thing on the camera. Almost the whole thing. So this is the list that I got from going through the problem sets. It didn't take too long to do. I think that took about like an hour and a half. And from that, I got some questions. Now, I think maybe I want to go through and look at questions to redo for problem sets 1 to 4 real quick, because I didn't include that when I was going through the first pass. And I think that would be wise. I did questions to do, but not questions to redo. Let's just go to problem sets. So problem set 1. Okay, I think I want to redo. Let's go problem set 1. Real quick, problem set 1. This was fine. 4. So I'm going to put 1.4. And I would put 1.6 from problem set 1. Let's go problem set 2. All right, let's do 2.1 again. Let's do .4 there. 2.5. Which one was this? B3. B3. Three, and I will say N2. I'll just do all of the B all. B all. And this one's fine. 7. Yeah, 2.7, I think. Should be done. And I don't think I'm going to do 8. Your operators. This is fine. 2. I think. Yeah, that would be a good one. So 2. This is 3.2. C and F. F and H. Zero, blah, 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 phase 4. 1, don't need to do. Let's go back to 4. Okay, let's do 4A. 4.2A. A, B. Yeah, it's just. So I'll just put, yeah, that's good. 3. Just forgot a phase there. F. Yeah, 3. Let's do 3. I don't know whether this one I kind of remember. I'm going to remember the answer, so I'm not going to do that one. And then let's do 5. Is it the last question? Let's do 4.5. Just because it will be a bit easier. So, all right. Let me just put this back here. So this is my kind of list of things to do. I've written a bunch of questions and a bunch of questions to do and questions to redo. I've also done a bunch of concepts. Some of these are going to be they're going to overlap. So I think given that I'm redoing some of the problems, I may not do as much Feynman technique because some of the stuff is going to get resolved by redoing these problems and seeing if I've learned it. So I'm going to try to pick out higher level concepts here. I'm going to also make a little section here for lectures because there's some concepts from the lectures that I found difficult, and I'd like to go through a little bit more patiently, kind of like a Feynman technique. And so let me just open up the lectures now to go through where I made notes for that. Let's do let me go back. I think I want to go to, let's go through lecture 11. This stuff seemed okay. This stuff seemed okay. Also okay. Yeah, I think that's okay. What lecture is this at? Resonances and scattering. So I'm going to do lecture 14. I have a note here from minute 36 to 57. And what is being discussed here, I think, is this is the phase. So this is related to phase. Okay. Scattering matrix. I think that made sense. Yeah. Okay. 3D harmonic oscillator. Angular momentum. Which lecture is this? This is lecture. This is the same lecture. This is also lecture 14. Lecture 15. Lecture 15. Lecture 15. And momentum. I'm going to say around 109. Lecture 16. This is our ladder. I'm going to say lecture 16 is ladder 2. Again, in momentum and the L plus minus operator. This is still lecture 16. Yeah, 16. Also from 104. This is where we get the images, I think. Spherical harmonics. Image. 104. Central potential. Yeah, I think this needs to be done again. Left 17, central potentials. Spherical well, Coulomb potential. Same thing. Make a note on this Coulomb potential. Yeah, maybe do central potential. I have the same abbreviation, central and column. Put your pencil out here. Okay, multiple particles, lecture 19. Identical particles. And this is 20 is periodic. Two. All right. All right, so I think this is what I want. Now, I've made this big list. I made this big list of things that I'm looking at. Now I want to kind of convert this into, this was just sort of like the brainstormed list. Now I want to convert this into a smaller list where I've got something a little bit more manageable, and then I can kind of pick and choose from there. I'm not going to have time to maybe do every single thing here. The problems I'd like to do again, I think I'm going to have enough time to do the problems again. And that would be maybe where I'd want to spend the majority of my time. But there's definitely some areas here that I'd like to spend some time on, maybe a couple days. And then these questions, yeah, the questions take a long time, so it's hard to say exactly, but definitely have more possible work here than there is time available. Reed is asking, do you think self-studying would be more fun, engaging, easier if there was someone you could ask questions to? Definitely it's easier to learn if you don't understand something. You're like, why is it like this? And then someone can explain it to you. So that is a challenge. And that is something that for a class like this is particularly hard. There are some places where I've had questions where I'm like, why is that the case? Why is that true? And it's not really forthcoming because I don't understand it, even though maybe perhaps other people do. So one of the examples is when I was working with identical particles, I was confused as to why the fact that they're identical particles would sort of change their physical properties. That to me seemed, well, why the identical particles is kind of what we think about them. That shouldn't change their physics. You know what I mean? Like if you're thinking about the real world, just because you have two apples and they're identical doesn't mean that they interact with each other differently than if one of them had a small blemish on it or something like that. But that's an example of like where I'm not really understanding the definition and it would be good to ask questions. But on the other hand, the nice thing about doing this sort of self-studying, even if you have to do it on your own, is that you really have full flexibility, full control over what you want to do. And I think in some cases that can be a powerful advantage as opposed to a disadvantage. So I think for classes that are much harder than your ability level, it's probably a disadvantage. But if you were if you were able to understand things as they were discussed in the lecture and you just had to practice them, then it can often be an advantage. So during the MIT challenge, I think it was an advantage to be able to do it that way. So I'm going to just start transferring some things over. I think I can switch the camera over to this view right now. And I can just go, this is going to be my new list of things to work on. So I'm going to have questions. 1.4, 1.5, 1.6, and I'm going to circle the ones that I have not done yet. Uh, 2.1, 2.4, 2.5b, and yes, of course. Well, we're studying bosons and fermions here. B and 2.7. I have 3.2 CFH. Then I have 4.2 AB. AB. And then 0.4, which I have not done. 4.5. And then I have, what's it down here? 5.1. 5.3 B, C, 5.4. And this is going to be 5.4, and then we're in 6. Did I want to do any reduce for 6? No. So it's 6.4 C, 6.5 A, E, 6.6 G, I. Now I have 7.3 B, C. 7.4 C, 5, all, I think that's it. And I have 8.1 C, 8.5 A, 8.6, 2 A, 5.4 E, F. And then we have 10.4 all, 10.6. Oh, I should have put 10.6, I bet. 10.5A and 10.7. So these are questions that I wanted to do. Yeah, so I understand the idea behind identical particles, that you have fermions that can't occupy the same state and the bosons which would even like to occupy the same state. So that was sort of the outcome of that analysis. But the thing that I was confused at is that it hinged upon whether swapping the particles should produce a negative phase or a positive phase. And that just, to me, like obviously you can observe those characteristics in particles, but the fact that you can't tell them apart seemed to be part of the physical logic of it, which was something that is something that I didn't quite understand. Why if it was, you can't distinguish the two of them, it would behave as some kind of physical difference in that sense. So swapping them Yeah, because if you have the fermionic particles swapping them, they pick up an overall minus sign on the wave function. And so if it equals its own minus, then it's going to equal 0. Whereas bosons, they get a plus sign. But I just don't understand how the physics is coming from that kind of identical description. Other than this is just sort of brute force. This is what we observe. So let me figure out what I want to do for concepts. So I'm going to now put this into my categories here. So concepts. So facts, I'm going to put various operators, and I'm going to think of an plus 1 half W. Yeah, well, obviously we observed that bosons are, but I guess the point that I was trying to, like, the thing that I didn't, is that the way that it was presented in the lecture is that there was clearly a connection between the fact that these particles were identical and this bosonic or fermionic statistics for the particle. So this was the thing that, like, that was the connection that it just sort of omitted me. Like, of course you can say, okay, that it obeys this property, so therefore you must have, these ones are identical under this swapping condition or that swapping condition. It just seemed to be, in my mind, just sort of, I felt like I was missing a piece of the concept. So, all right, I'm going to write down some of these identities here. I want to have, let's go L squared Z plus minus A various operators. Let's get some other stuff here. Finite well. Step. This is going to be step. Infinite well. Finite well. Simple harmonic oscillator. Central. Cool. Integration. Exponentials. Jones. Hyperbolic. What else do we want? Skills, dimensional analysis. chemical particles. It's, well, stall momentum. This would be what? Let's do the depth of the dot product. Adding 0, integrating by parts, Taylor expansion. Substituting variable. Delta function. Normalizability. Spreading R naught, G naught, G naught formula. What else do I have? Commuting through, I think I've got that. I'll just put it here anyways. Commuting through. Working with limits. I'm going to put this actually over here. Operators on transforms. Concept. What else do I want? Relation. Oh, cat's back. Dimbroli. I think I get that now. I get that now. Remember that. formula. What else do we have here? Did I put that over here or here? No, I'll put that here. Real energy. Is there anything else that I wanted to do here? Oh, change order of integration. I'm adding 0. Integrating by parts. Hello, cat. Yeah, I'm just push you a little forward. There you go. All right. I think that's good. I'm sure there's some other things. So I'm just going to put units. Operators. Constants. All right. So I have now reduced this to a to-do list here. So I've got some problems that I want to redo. This is probably about, let me look at, I think each question had about, let's say about, probably about 6 to 8 problems. So if I look at this, I'm doing about maybe a third. This is probably, I would say, like roughly 3 problem sets worth of work. So given that it's roughly 3 problem sets worth of work, I've been going at a pace of about, I'm trying to remember how many I was doing, maybe about one. So we got probably about 3 days here of work for sure. And how many days do I have left? Let me just check my schedule here so I can look here. So not including a day, I've got 1, another 5, 6, 7, 8. 8 days, assuming I don't do any weekend days, which I'm not planning on doing. But I mean, if I really feel like pushing it right at the end, I might do a weekend. So given that I got 3 days about here, so that gives me about 5 days left. I'd like to have maybe 2 days for just focusing on about 5 days just about 2 days just for focusing on kind of exam prep, looking over past exams that don't have solutions, testing myself under some exam conditions. Normally in a class, I do a little bit more of that testing under exam conditions, but I think it's just getting all of this done is going to take precedence, I think. So I wanted probably about 2 days for exam prep. I got 3 days for this, more or less. So that gives me about another 5 days. So I think what I might do is I might interleave it. Oh, okay, don't step on the keyboard. I might interleave it where I will do some concept stuff and then go back and do some problem sets. So I won't just do 5 days of this and then just go 3 days and do it like that. So I think what I'll probably do is for tomorrow, at the very least, I'll start working on some of these. I still have a little bit more time today. I could go into doing one of these. There was some stuff in the lectures that I might do, so I might take a little break and then come back and do maybe lecture 14. It's not going to be a whole heck of a lot right now, but it's still a little early to end the day. And so looking at that, I think if I spend I'll do maybe 1 day on, 1 day off for each, switching back and forth, and then just sort of see where I'm going. But this is going to be my new to-do list. So before I was trying to get through all the problem sets. Now I've got this kind of to-do list, and I'm hoping that I can get this done in, I think I was saying about I had 8 days left, so, and I want 3 days here, and let's say 3 days here. So I definitely don't want to do more than that. So if I spend the next 6 days alternating between these, so I have a day of problems, a day of this, should be able to get it all done, and then there'll be 2 days left that I can focus on both getting ready for the exam and actually writing it. Yeah, I feel pretty good about that. I think if I retook these problems, I should be okay. Some of them are new, so those ones are going to take a little bit longer, and I might have to get some feedback on them. But I'd like to work through these guys first. I've also been wondering whether I want to look at some of the lectures for 803. So there's some ideas here that I think are very much 803. This dispersal relation is very much 803. I'm wondering whether stuff with phase might be 803, but I don't know whether I could locate it in the class without watching all of them. Because watching all of the lectures from 803 is going to take at least 2 days, and I just don't know whether 2 days is going to be pretty costly, I think, in terms of missing these things out. So given that I only have this many days, I think doing this is probably best, sticking to what we have. You'll notice I divided this into concepts, facts, and skills. So these facts, I think I might write them all out first and then just sort of test myself a little bit on some of these. So this might be a little bit of time to do this. Not too much though, but I might do this first. Just get these all written out, kind of make my own formula sheet sort of, except I'm going to probably want to divide it into 2 parts so I can cover up half of it and do some active recall to try to remember it. Skills, I need to just practice this. It's going to be hard to find exact solutions. So I think some of these skills are going to get retested here. So that's kind of why I also wanted to redo things, is because I wanted to recheck some of these skills. Some of them, I think what I might do is, even though they're a skill, and so they're really something you practice as opposed to kind of analyze conceptually, I might do little Feynman techniques for them, just so that the kind of idea of why you're doing certain things is motivated. So for these things here, I might just kind of do a little Feynman technique of explaining it so that when I get to these problems, that's how I'll work on it. Yeah, okay. So I'm going to take a little break right now. I'm probably going to be back in, let's say, half an hour. So that would make it 4:15. And then I'll try to go till 5:30 to 6-ish. I'll work for that. So I think I'm going to start working on Feynman techniques. I think I'm going to go through some of this stuff from the lectures. So I'm not going to go straight from this list right now. I think I want to go through some of these lectures where I made some notes about I didn't understand this fully, just because that is related to the stuff on here. But I think that there's also now it's going to look different having done the problem sets. So I might just kind of rewatch them, sort of retake the notes and just sort of see if they still feel confusing, or if I feel like, well, now that I've done the problem sets, they make sense. So I'm going to just end the stream right now, but I'll be back in about half an hour. I'll read saying the dispersal relation versus how fast a wave moves, function of its shape. So that's what I got from doing the problem set, that you have this WK relationship. So it's basically depending on the wave number, but there was a bunch of math involving this. Like they just gave me a formula, which I'd never seen that formula for because I'm pretty sure it's from 803. So I think that I'd like to maybe find the lecture from 803 where they do the dispersal relation and watch it rather than just try to guess at the formula and the meaning and this kind of stuff when working through the problem. So that's an example of something I might be able to go back to 803 and just do, because there'll be a lecture that will probably talk about the dispersal relation because it's a very identified concept. Whereas stuff involving phase changes and this kind of stuff, I think that's kind of a whole class 803 concept. And so I just don't know whether I'm going to get much bang for my buck going back through that. All right, so I'm going to take a little break. Usually derived from the partial differential equation. So thanks. Okay, thank you, Reed, for helping me out. Reed's helping me out with a few concepts here. I appreciate it when you plug into the EDIKX. Yeah, so if you have any, if you know any of this stuff and you're listening to this, feel free to give me some advice, some hints. I am doing this mostly on my own, just mostly with the resources, but I am not against getting help if you think you see me struggling with something. So I'm gonna leave right now. I'm gonna be back in about half an hour, and then I'll work for another hour and a half or so.